Last time we learned how to integrate a function f of two variables over a polar rectangle, which is a region that looks like this. This region R consists of all points r comma theta using polar coordinates such that R is between A and B and theta is between alpha and beta. This special type of region is called a polar rectangle. And we have learned a special formula for integrating a function f over a region R, which has this form. And now we're going to learn how to integrate over a more general type of region, which is called a polar region. And a polar region is a region D that looks like this. And this region D can be described like this. D consists of all points r theta using polar coordinates such that theta is in between alpha and beta, and r is always in between h1 of theta and h2 of theta. So the equation of this lower curve is r equals h1 of theta using polar coordinates. The equation of this outer curve is r equals h2 of theta using polar coordinates. This special type of region is called a polar region. And just as a polar rectangle is analogous to a rectangle, a polar region is analogous to a type 1 region. And so our situation is similar to what we did earlier when we had to learn how to integrate a function f of xy over a type 1 region. At that point, we already knew how to use Fubini's theorem to integrate over a rectangle. And then we had to figure out how do we integrate our function f over a more general region, which is a type 1 region. Well, now our situation is analogous. We already know how to integrate a function over a polar rectangle. We have a special formula to do that. And now we have to figure out how do we integrate our function over this more general type of region, which is called a polar region. And the trick, if you remember the trick that we used to integrate over a type 1 region, what we did is we just found a larger rectangle which contained our type 1 region, and we extended the function f that we're integrating, we extended it to be 0 so that our function was now defined on the entire enclosing rectangle. And then we just integrated over that rectangle using Fubini's theorem. We're going to use a similar trick to integrate over this polar region. What we're going to do is we're going to introduce a polar rectangle which contains this region. So let me just draw this curve here and this curve here. And now what we have is we have a polar rectangle. Let me call this polar rectangle R. It's a polar rectangle which contains the region D that we want to integrate over. And let's say that our goal is to compute the integral over D of a function f. What we're going to do is we're going to extend this function f. We're going to introduce a new function, which I'm going to call capital F. And capital F is going to be equal to lowercase f everywhere inside this region D that we want to integrate over. And capital F is going to be equal to 0 at every point in this polar rectangle R, at every point outside of D. So what we are doing here is we're just extending lowercase f by defining it to be 0 outside of D. And notice the integral of lowercase f over the region D is equal to the integral of uppercase f over the region R. That's because uppercase f is equal to 0 everywhere at every point outside of D. So in this integral here, there's no contribution coming from the region outside of D. The only contribution is coming from D. So we may as well, here in this integral, we may as well be integrating over D. But on the region D, capital F is equal to lowercase f. So that's why this integral is equal to this integral. Now notice we can evaluate this integral using the special formula that we developed last time. This is equal to the integral from alpha to beta of the integral from A to B of f of r cosine theta, r sine theta, r dr d theta. That's the formula we developed last time for integrating over a polar rectangle. And what are A and B? Well, A is this inner radius, and B is the outer radius for this polar rectangle R. That's what A and B are here. Okay, but let's look at this inside integral. Here we're integrating from A to B. For a given angle theta, we are integrating from A to B. And the function we're integrating from A to B is this function capital F. But notice this function capital F is equal to 0 everywhere along this little line segment, and it's equal to 0 everywhere along this little line segment. So instead of integrating all the way from A to B, we might as well just integrate from here to here, because it's only in this range that capital F is non-zero. So this can be rewritten as the integral from alpha to beta of the integral, and then the starting value of R is h1 of theta, and the stopping value of R is h2 of theta. So here we're going to integrate from h1 of theta to h2 of theta, and then the function that we're integrating is f of r cosine theta, r sine theta, r dr d theta. And why do I have lowercase f here instead of capital F? That's because at every point along this range, at every point along this line segment, capital F is equal to lowercase f. That's why I have lowercase f here. And this is our formula that allows us to compute an integral over a polar region. This formula, this is the formula that we're going to use to integrate our function f over a polar region. If you graph the equation r equals cosine of 2 theta using polar coordinates, then you get this shape. It looks like a flower with 4 petals. And what I want to do now is compute the area of this first petal of this flower. We want to compute the area of this region here, which is shaded red. This region, let's call it D, is the first petal of our flower. And the area of D is equal to the integral over D, the integral over this region of the constant function 1. So we have to evaluate this integral, and we're going to do this using polar coordinates. So this region shaded in red, this region D, this is a polar region. This region D can be described as the set of all points r comma theta using polar coordinates such that theta is always, if you look at any point that belongs to this region shaded in red, you will notice that theta is always in between minus pi over 4 and pi over 4. So minus pi over 4 and pi over 4. And also r is always in between 0 and cosine of 2 theta. Our region D can be described like this, and this shows how you can view D as being a polar region. And we know how to integrate over a polar region. So let's just use the formula that we discovered for integrating over a polar region. According to that formula, the integral over D of the constant function 1 is equal to the integral from minus pi over 4 to pi over 4 of the integral from 0 to cosine of 2 theta, and then 1 times r dr d theta. Okay, this is now we just have to compute this iterated integral, and then we'll be done. We need to evaluate this integral, so let's start by doing the inner integral. What's an antiderivative of the function r? Well, it's r squared over 2. So let's take our antiderivative and evaluate it from 0 to cosine of 2 theta. And when we plug in cosine of 2 theta for r, we get cosine squared of 2 theta over 2. And when we plug in 0 for r, we get just 0. So the inner integral is equal to cosine squared of 2 theta divided by 2. So that means that the area is equal to 1/2 the integral from minus pi over 4 to pi over 4 of cosine squared of 2 theta d theta. Now this integral might seem difficult because what's an antiderivative of cosine squared? But there's a trig identity we can use at this point that will help us out. There's a trig identity that says cosine squared of u is equal to 1 plus cosine of 2 times u over 2. And we'll prove this identity later. For now, let's use it. Let's apply it to simplify this term. If we plug in 2 theta for u, then we discover that cosine squared of 2 theta is equal to 1 plus cosine of 4 theta divided by 2. So the area that we're trying to compute is equal to 1/2 times the integral from minus pi over 4 to pi over 4 of 1 plus cosine of 4 theta over 2. So that makes the integral much easier, having applied that trig identity. Now let's pull this factor of 1/2 out front. So we get 1/4 times the integral from minus pi over 4 to pi over 4 of 1 plus cosine of 4 theta d theta. Now what's an antiderivative of this function? An antiderivative of 1 is just theta, and an antiderivative of this function here is minus sine of 4 theta over 4. You can get that by using u substitution. So now let's take our antiderivative and evaluate it at the endpoints. So we're going to evaluate our antiderivative from minus pi over 4 to pi over 4. When we plug in pi over 4 for theta, we get here pi over 4, and then here, if we plug in pi over 4 for theta here, we get sine of pi, which is 0. So we have no contribution there. Now, what happens when we plug in minus pi over 4 for theta? We're going to get a minus pi over 4 here. And when we plug in minus pi over 4 for theta here, we have sine of minus pi, which is 0. So this is what we get. And this, when we simplify this, is equal to pi over 8. So that's our final answer. The area of the first petal of our 4-petaled flower is pi over 8. Now let me prove this trig identity, which says that the cosine of u squared is equal to 1 plus cosine of 2u over 2. There's a more basic trig identity, which tells us that the cosine of 2u is equal to cosine squared u minus sine squared of u. And we know that sine squared is 1 minus cosine squared. So this is equal to cosine squared u minus 1 minus cosine squared u. And that is equal to 2 cosine squared u minus 1. So now just isolating this term, we discover that cosine squared of u is equal to cosine of 2u plus 1 over 2.